In this video, you will learn about the refraction of light at a spherical surface. A typical scenario would consist of two different media of different refractive indices separated by a spherical interface of radius of curvature r. The object could be in one of the medium and the image could be in any of the medium. In this example here, the object is in the rarer medium and it forms a real image in the denser medium. So our goal is to find a relation between the object distance, image distance, radius of curvature, and the two refractive indices. Such a relation would be called the expression for refraction at a spherical surface. This relation would be used twice to come up with the derivation for the lens maker's formula, which in turn is used to design lenses as per the doctor's prescription. So such lenses are very useful and invaluable for people who are suffering from myopia or hypermetropia. So that these lenses are the difference between vision which is blurred like this and clear like this. So what are the different possibilities when you start the derivation? The interface could be curved with its convex side on the left or concave side on the left, and the two medium on either side could be rarer here or denser here, and vice versa. And throughout our derivation, we'll be following the right-hand Cartesian sign convention, according to which the object has to be placed to the left of the optical element, in this case the interface, and the incident rays will, as a result, always move from left towards right. So now all distances have to be measured from the center of the interface. So you could imagine a measuring tape whose 0 point is placed at the center of the interface, and then it has to be pulled towards the point whose distance we want to measure. So for example, we want to measure the radius of curvature here, put the 0 of the measuring tape here, pull it towards the center of curvature. The motion will be in the direction of incident light, incident rays, so it would be a positive measurement. And if you measure the center of curvature in this case, you have to pull the tape opposite to the direction of incident rays, so this radius of curvature measurement would be negative. Now we make the following assumptions during our derivation. First is that the object is a point object situated on the principal axis. This makes the derivation very simple. The second assumption is that the aperture of the refracting surface is small, such that only incident rays very close to the principal axis need to be considered. So this is vital so that we can make use of the third approximation, which is the small angle approximation. So according to this, for small angles like less than 5 degrees, the value in radians is almost equal to the sine of the angle and tan of the angle. As you can see, for 5 degrees, they are equal to first 3 decimal places, and for 10 degrees, they are less accurate. They are equal only up to first 2 decimal places. Then we make use of this geometry property that the exterior angle is equal to the sum of the interior opposite angles of a triangle. So let's get on with the derivation. So this is a spherical interface which separates an optically denser medium from the optically rarer medium surrounding it. This is the center of the spherical interface. And a straight line passing through any point on the interface and the center of curvature would be called as the principal axis. So let's say the object is placed on the rarer medium and it's a point object on the principal axis. So the normal would be the line passing through the center of curvature and point of incidence. And angle of incidence is the angle between the normal and the incident ray. And since it's going from rarer to denser medium, the refracted ray would bend towards the normal. In this case, it has bent so much that it forms a real image on the principal axis. The reason I know that the image would be here is, if you consider another incident ray which is along the principal axis, it would make an angle of incidence 0 with the normal, which is also the principal axis, and so it would go undeviated and meet this refracted ray here. So the other case which is possible is this refracted ray bent much lesser. As a result, it would still be diverging compared to this other ray which is along the principal axis. So then if you extend them backwards, they would appear to meet at a point on the same side as the object in the rarer medium. So that would result in a virtual image. So we will try to do that derivation next if we have time. We will end up with the same result whether it's going to form a virtual image or a real image, because we are going to use the proper sign convention when we use the object distances and image distances and radius of curvatures. You will see as we proceed. So object distance in this case would be negative, because you have to start the measurement from the pole, which is the center of the interface, and when you move the measuring tape away from the pole to the object, you are moving it in a direction opposite to the direction of incident rays. So it's a negative measurement. By the same logic, image distance would be positive and radius of curvature would also be positive. So we will be calling the angles made by the incident ray, refracted ray, and the normal or radius of curvature as alpha, beta, and gamma. And the refractive index of the rarer medium is mu r, and of denser medium is mu d. And we will start our derivation with the Snell's law of refraction, because refraction is what is happening in this case. So the refractive index of the first medium multiplied by the sine of the angle of incidence is equal to the refractive index of the second medium multiplied by the sine of the angle of refraction. We use the small angle approximation to replace sine I with I and sine R with R. And then we use the exterior angle property to substitute for angle of incidence I and R respectively. Here, this is how we do it. Look at this triangle. Here I is the exterior angle and alpha and gamma are the opposite interior angles. Similarly here, gamma is the exterior angle, and look at this triangle. So beta and R are the opposite interior angles. So we rewrite it in terms of R, and then we again use the small angle approximation so that we can move from angle to distances, because tan alpha and tan gamma, when you use, you will incorporate distances or lengths of the triangles, sides of the triangles. So from alpha, when you go to tan alpha, you get the chance to replace the angle alpha with some sides. So here also gamma will be replaced with tan gamma and beta with tan beta. So now you see the interesting part. Tan alpha is opposite by adjacent. So opposite is a side H, and it is supposed to be very small because of the small angle approximation. And the foot of this perpendicular will be very close to the point P, so that the base of this right angle triangle is almost equal to OP, which is the object distance. So the base of this side can be replaced with U, but then U is supposed to be a negative number according to our sign convention, but this ratio has to be a positive number because this angle is a positive angle. So we put a minus sign so that it makes mathematical sense. Similarly for tan gamma, opposite is H, by adjacent is radius of curvature R, which is positive in this case, so we don't have to put a minus sign here. Similarly here also we don't have to put a minus sign for R and B because they are already positive. So now if you substitute this expression for I and this expression for R, you end up with this. H will cancel out, and then you just rearrange the terms and you end up with the result, which is the beautiful formula of refraction at a spherical surface. You can see the symmetry here, mu d, mu r, mu d, mu r. So that will help you to recollect it. Now let's do the derivation quickly for the virtual image case. You will see that the steps are all the same. Only difference is this refracted ray is making a much bigger angle of refraction. As a result, the image would be a virtual image on the same side of the object. Rest are all same. This time object distance and image distance both are negative, whereas the radius of curvature is positive. So rest are same steps you have to follow. Now you see here the result is again the same. Hope you enjoy the video.